Alright, hell yeah. So my buddy emailed me, you know what I mean? It's like, I don't know the double slit experiment, and I'm sure other people don't either. So, can you inform me? And yeah, well, what the hell's going on? Okay, so we got a little notes. Let's see what we got. One photon, you got one photon in the room and 3 people. One person sees the photon. Can the other 2 people see that photon? Hell no. Because it's like if you had one orange in the room and 3 people and one person ate the orange, can the other 2 people eat the orange? No. Okay, so but then everyone's talking about light. It's like, well, light's a wave. Well, yeah, if you got a lot of oranges, you know what I mean. Let's say you just have like a pyramid of oranges so tall, and we're looking at this from outer space. It's like the pyramids, and all of a sudden you get an earthquake, and all these oranges, well, you know what I mean. Pretty soon they're going to make like a ring out here. Like all these oranges that were piled in the middle are going to make a ring out here, and it's going to be, let's say, half the height of the pyramid. And then the earthquake keeps going, and the oranges keep rolling. You know what I mean. So now they're out here, and guess what? This is only a quarter of the height of the pyramid. And why is because you had like a bunch of oranges. And out here, sure, you have the same number of oranges, but you have to like cover this distance. And so now I think we understand what light does, you know what I mean? So, but you had to have a lot of friggin' oranges. Because let's say you're just talking one photon, you know what I mean? Now you got one photon. Well, 2 things happen. This photon can only go in one direction. You know, speed of light, but only in one direction. This thing ain't going in, if you have this, let's say you're like, well, how about 4 directions, you know? You would literally need 4 photons. You know what I mean? If you start with 4 photons right here, sure, they can go in 4 different directions. You know what I mean? If you start with 2 photons, and you know, they might go in those 2 directions. It don't, you know what I mean? So if you got 1 photon, it just goes in a single direction. And now here's the deal, because this is our room, and we got the 3 people. You know what I mean? And you know, these guys are probably doing, you know, smoking weed, playing video games, or whatever. But anyway, this is the healthy guy, and he's like, hell yeah, I'm going to eat that orange. And so, hey, this orange, he goes to the orange, or the orange comes to him, and then he just gobbles it up. You know what I mean? And guess what? No more orange. And same thing with photons. You know what I mean? If you have a photon in the room, and you see it, no more photon. I don't know what I was getting there, but if you have a laser, and the laser shines the light on the wall, and in any normal situation, you're not going to see the laser. But if it's like a really dusty room, you'll see the laser. Guess what? The little point of light that you actually see in your eye, well, is now in your body. You know what I mean? You transfer that energy into your eye. It's now in your body. That piece of light that you saw is no longer hitting the wall. All the light pieces that you saw. So if you see all the light because of a dusty room, well, guess what? Those pieces of light did not hit the wall. They hit your eyeball, and now they're in your body. You know what I mean? That's how trees grow. You know what I mean? You know what I mean? You see the light, and so does the tree. Why? Is because the sun is just a photon generator. Well, we're talking 10 to the whatever, make up a number. Is it 10 to the 10? Is it 10 to the 100? I don't know. It's in between 10 to the 10, 10 to the 100 photons that sun's generating. You know what I mean? Every so little often. Okay, so I think you get that part. So let's move on. Are the waves you make? Oh yeah, this is more philosophical. Like, how about you for your life? And let's throw some more time on the clock. All right, hell yeah. Like your life. Are you? You know what I mean? Or are you the waves that you make? For me, it's literally the waves that I make. And you know, you ever go to like an old people's home? I think that's what they call them. They're like, yeah, I live in an old people's home. But you know what I mean? It don't look like, you know, like an old guy. You're like, whoa, don't look like he can make no more waves. He can hardly eat his pudding. You know what I mean? So you're just like, I don't know. It don't look like you did nothing. You know what I mean? Because right now, there's no way you can make waves. But anyway, so I think if you look at it like that, you know, it's not so scary, this double slit experiment, that, you know what I mean, we wrap our minds around, you know, things being concrete and stuff. You're like, okay, you know what I mean. But okay, so that was the metaphorical. Let's move on. Yeah, this is cool. You go into a cave. You know what I mean? It's total dark in the cave. You ever got the opportunity to go into a cave, turn off all your lights, whatever. It's crazy because you're just, okay, it's totally dark in here. But guess what? You got two rocks that are all like flint. You could bash those rocks together, and what are you going to make? You make some light. Okay, so how about, let's say you're just in the farthest reaches of the universe, and there is no light, and you're not even there either. Can you generate light in whatever, you know what I mean? No, you can't. So in a cave, you can generate light from matter. So light is energy, so you can get energy from light. So this talks that you had to have mass. If you're in a cave with total darkness, to get light, you had to have some sort of mass. You either brought in a battery, has mass. You either brought in, you know, a lighter. Fuel has mass. You know what I mean? And or you brought in the rocks with the flint. So you need mass to generate light. And all light is the electromagnetic waves. It is just energy. You know what I mean? It's energy in wave form. And so I would Google right now electromagnetic waves, and you'll see, hell yeah, it's a spectrum. We're just so light sensitive because that's our eyeballs. Our eyeballs can pick up photons and absorb them, and then get the information from them. You know what I mean? But it's just a spectrum. It's just a wavelength of electromagnetic radiation, electromagnetic waves. Because else you got like X-rays. No one gives a hoot about those unless you break a bound. And then radio waves are on the low spectrum. And you know what I mean? And yeah, I just made a joke because it's 2023. No one gives a crap about radio waves. Save myself $1.50. Okay. But we're all interested in light. You know what I mean? There is no woo-woo culture for be like, whoa, yeah, do you... You know what I mean? Like, I do radiotherapy. We just listen to, you know, NPR. You know what I mean? I think most people get their therapy that way, too. Anyway. Yeah. Can you have a single wave of light? Okay, so now let's talk more about this one photon. Because that's cool. Because, okay, so the photons from the friggin' sun... I mean, they're in a wavelength, and they finally reach the Earth. But we're talking a lot of particles. And yes, they're going in all directions, and it's so dense. Like, let's say this was our oranges, and you know what I mean. And so, like, right next to the sun, hell yeah, it's crazy. You know what I mean. And then out here. You know, and then by the time it gets to us, it's like, booyah, we can take it, you know what I mean? A tree only uses 10% of the actual sunlight during high noon. And, you know, we got to be that far away from this energy source. Okay, but let's talk about the individual photon. Because let's say, and then, because if you do have a mass, let's get back to that. Let's say you have a mass, so this is a little mass, and it can generate only one photon. Okay, so that's the thing. If you're talking Newtonian physics, if you a piece of mass has to, you know, has to be in a three-dimensional state. This is 3D. So if you have a photon generated from this side of the mass, it's going to be traveling this way. And if it's only one photon, you know what I mean, it's going to make a little wave like this. And then we'll just cut it off. And you know what I mean? And I don't know if it's like, you know, like this. You know, that's kind of what some of the pictures are. But this would be one photon. So let's say you have one photon. It got emitted. And it's traveling at the speed of light, which is 300... it's just 300 million meters per second. Nothing too fancy. You know what I mean about that? Can't go faster, so I guess it is pretty fancy. This literally should be the one. You know what I mean? If anything should be labeled number one in the whole universe, it would be this speed of light. That should literally be the number one. And then everything, we should just be a fraction of that. But that's for another video. Alright, let's throw some more time on the clock. Alright, hell yeah. And if this mass can make 2 photons, well, they're going to go in 2 different directions. If it can make 4 photons, it's going to go... If it could just make a sun load of photons, well, guess what? Even just right here, you're going to have hella, and they're going to be going this way, you know what I mean? And then you do have... okay, so then the other thing. If you're in space, theoretically, these photons only go in straight lines. They don't scatter. So, I mean, if you're talking... So again... You know, why you can see the light from the sun at 360s because we're traveling around the sun 360 days a year, is because the sun is just boatloads of photons on all surfaces. And it's a round surface, so they're just hitting every, single normal direction, perpendicular to the surface of the sun. And, Yeah. And the boatload of photons. I mean, and so I don't think it's hard to see if you got the sun and you were right next to it, you'd be like, whoa, too many photons, dude, too many. And then if you were like out here, you're like, well, that's, you know what I mean? Whoa, now we're getting farther out here. Do we have enough photons? Sure, because that's where Earth is. You know what I mean? So we get plenty of photons from the sun without getting just vaporized. Okay. But it's a... Alright, so I think that answered some questions. We gotta friggin' move on. And I think that's that page. So we just got a couple more pages. Oh, there's my jokes for my next comedy set. Hell yeah. Okay, so, now, what is a wave, though? Because you have ocean waves that kind of crash on shore, crash on the beach, and these happen every 3 seconds. They're not traveling at the speed of light. And so these are the shorter waves. Some of the longer waves, like out into the ocean. Oh, so these are traveling at like 10 kilometers per hour. That's the only. I don't even know what the hell that is. But bigger waves out in the ocean, they'll travel faster. They have a longer wavelength, and they'll travel 50 kilometers per hour. So that's pretty impressive. But because they're so long, you could have like 1, 2, 3, you know what I mean, little waves by the time this wave actually hit. So the bigger waves come every 14 seconds. Cool. And then tsunamis, they don't come every, you know what I mean, 100 seconds, but they travel at 800 kilometers per hour. So that's 80 times as fast. And then they're really long, you know what I mean, hell yeah. So you got it, big packet of energy. Alright, so is that what the hell I even wanted to talk about right now? I think we're losing it. Oh, yeah. Okay, let's talk about this, because we talked about electromagnetic radiation, and we're familiar with mass. This is a hydrogen atom. Hell yeah, it's got mass, and it's got hella energy, E equals mc squared, you know what I mean? We know that. And then you got like 1 photon. Well, it also has energy, it's traveling in a direction, and yeah, so its energy is, I don't know, in joules, it's like 10 to the negative, 22 or something, and then so that's why you have to have a lot of them to actually get like because how much, it's 10 to the 6 joules, 1,000,000 joules is in 2,000 calorie diet, so you have to have a lot of photons to actually, you have to have a lot of photons to actually get the energy, and that's why the sun just makes a ton of photons. So anyway, mass doesn't move, but it's still bound. It still has energy due to the E equals mc squared equation. All right, I think we're basically done, and then we'll go back to the double split. Yeah, that was good enough. You know what I mean? I guess that's all the thing I wanted to do. But anyway, so So even if you're shooting, okay, so here's the deal. So here's the double slits, and then here's the, you know, it's kind of going to those two little areas. If you just shot one photon this direction, yeah, they're just going to land over here. You have your photon gun that you're able to shoot it, you know, right out of here, and like in between the slit, and you just shoot it, your one photon at the wall. Guess what? The wall's going to see it right there. And I think going back to like kind of like if you just shoot one photon, like the wall either gets to see it or you get to see it. You can't just see it, you know what I mean? It either hits the wall or it hits your eye. Oh, that's fascinating. Oh, I'll have to ask my brother about that one. If you have one photon that hits this wall, it gets absorbed into the wall. Well, I guess if it's a mirror, it could just get reflected back into your eye, I guess. Anyway. But you have to have I mean, we're talking these slits are pretty close together, and then you have like a huge beam of laser hitting these two slits. You know what I mean? So that's the scale. You know, we're not talking about, oh, I'm just like, I'm shooting, like, I'm taking like a dart style, one photon and throwing it through this slit, and then one photon over here, and then just magically getting a bunch of lines. Hell no. You're taking a huge sun-like slug of light and then hitting these two slits, would also have a width, you know what I mean? And you know, so anyway, so it kind of gets back to that. All right, hell yeah. Now I think it's truly important that you understand that from a scientific perspective, photons are massless, and they're approximately massless. I mean they're for all intensive purposes don't have a mass. Because anything with a mass has like kind of a three-dimensional, you know, aspect to it, where because a photon is massless, it's just a packet of energy. It's just a little wave of energy. You do with it what you want. If you grab it with your eyeball, you know what I mean, then great, absorbed into your body, and then you got some information about that one photon. You know what I mean? Case closed. So it is a wave in that set, but a wave is also hella energy, you know what I mean? So, I mean, you could power whatever we're powering. You charge your phone with it. And yeah. And then, so that's the difference between just an individual photon compared to, like, how about a mass? Because let's say you just have a little generator, which is just some copper, you know what I mean, copper windings, hella copper windings, maybe in a circle, and then you spin them, and then you have more wire in between, and guess what? I mean, you have a massive copper, and then massive steel, but you do this, you generate waves, and those waves have energy, and then you get electricity, you know what I mean? So the end product is the fascinating part, but the end product is still just a wave, you know what I mean? And these end products travel at the speed of light, so that is impressive. Mass, we understand, can't travel the speed of light. Small particles can get up to the speed of light, but you know what I mean. For all intents and purposes, we're stuck in a pretty slow, you know, moving, you know, Earth and universe, and you know, when it comes to that speed. But anyway. Photons, for all intents and purposes, are just energy. So here's, you know, even for my brother, and, you know, I don't mind saying wrong things, because it's just kind of where I'm at in my understanding. And sometimes, you know, having an understanding that's wrong helps you to get to that understanding that's right just much faster, as long as you're open-minded and not just a flat earther. Okay, so, you know, it's my understanding that, like when you're at the beach, maybe like laying down at the beach, and then just on the horizon, so I guess this is your horizon you see because there's some sand in front of you. Every once in a while you see like a wave pop up and crash, you know what I mean, and then it disappears, and then you see a wave pop up and crash, and then it disappears. So I'm comparing that to actually seeing like you got the sun on the horizon, and you're actually just visually seeing the light from the sun. And so, I mean, for me, this does help me, because it's just like, well, Is this actually, did the light actually travel from the sun? Because that's so interesting about waves, is waves get to travel at the speed of light. They can't not travel at the speed of light. It's just what they do. And then this goes back to any science. Science is based, I'm going to write the word phenomenon, but science is phenomena. If you can identify a phenomena, then great, we identified it. You know what I mean? It's nothing special. I think what trips people up is when they're just like, oh, well, maybe I fall into the trap of this. I just think, I mean, to make the sun more lackluster is the fact that, I don't know, let's just get to it. I believe that it's the same as water waves. You know what I mean? So here's the ocean, and then here's the beach. You know, finally a wave crashes on the beach. Did this water travel to the beach? Hell no. The wave did. So the energy form is what traveled. It wasn't the wave itself. Now, photons are massless anyway, so who cares? Who cares if it's the energy that traveled or the, maybe, maybe I answered my own question. Let's just do it, because it's just like, if you had the sun and the sun emitted one photon, and then you put your eyeball in front of it, even at the halfway point before it gets to the Earth, that photon's no longer there. It gets absorbed. Yeah, we might have to come back to that one. But a photon is also a subatomic particle. So you should look up subatomic particles, because the only two subatomic particles that pop up, you know, on online were photons and gluons. They're the massless particles. All the other subatomic particles, you know what I mean, kind of have some sort of mass element to them, is because they're usually made to form. So any subatomic particles that are used to form an actual atom, well, hell yeah, those are gonna, you know, have some sort of fundamental property of mass. But photons are not. They're essentially massless. You can have a tree which uses the energy to create, you know, other chemical processes, you know, with the carbon, and you know, it could be the energy to drive that. So it's just kind of interesting how mass can have energy, and then just a waveform has energy. I think it's really easy to see how a wave, you know, an electromagnetic wave has energy. You know, kind of harder to see how just a piece of, you know, hydrogen atom has energy, but E equals mc squared does have energy. Okay, so yeah, that was the whole thing. Okay, so yeah, just a ramble session, but those are the things that I would actually get more in tune with. You know what I mean? Watch some videos on electromagnetic waves, and you know how it's a whole spectrum. Oh, and then this was the thing, because if you change wavelength, you can do that instantaneously. Because I love Newtonian mechanics, because it's F equals ma. Like, I love the skydiver. You know what I mean? You're skydiving, and you're going to hit terminal velocity, because you have a force, and your speed's going to increase 9.8 meters per second. 9.8 meters per second every second. You know what I mean? And that's about 20 miles per hour every second. But you only reach 120 miles per hour. So, you know, basically in about 6 seconds, you know, give or take, you're going to be up to terminal velocity. But then there is no change in velocity. So that's pretty interesting. And why is that? Well, F equals ma governs everything in the universe, you know, from a Newtonian perspective. If it's an atom, if you got a three-dimensional atom, F equals ma. So that's saying that, well, if you stop, then you must have taken other mass and accelerated other mass at the same amount that your mass is being accelerated by gravity is 9.8. And that acceleration of the other mass is the air molecules. All the other air molecules that are hitting you are getting moved out of the way, and they're accelerating in all directions. And if you quantified all those accelerations, they would equal to your mass times gravity. So it's good to look at Newtonian mechanics. And that's my favorite one. I forget even why I brought that up. It's because that requires mass. And a photon does not have mass. Electromagnetic has no mass, and so there is no change in acceleration. There's no change in velocity. When a photon hits your eye, it just does. It's either there or it's gone. It's either, you know what I mean? It's either in space, you know, and traveling at the speed of sound, and the second it hits your eye, booyah! It's not over here. It doesn't go through your eyeball and just continue into like magical land. There's no change in acceleration. There's no change in velocity. There's no change in t by the moment it you know what I mean, hits your eye, and this wavelength is gone. So that is the cool thing about waves, is they do not have an F equals ma. They don't have to change. They don't have to decelerate. And I mean, even from my perspective, going through engineering, it took me even just a couple months ago to kind of realize that. It was just like, oh, there is no change in acceleration. And so that's where this video is really important, because we're just really touching the surface of basic concepts, and those are the ones that you want to be able to just have a normal conversation with. Because if you can't have a normal conversation, like even I struggle with it, but you know, we still try. And I do this because I know it's amazing. Because you're just like, oh yeah, I don't think most people could have a, you know, they could probably have an intellectual conversation. They're like, oh, I know this equation. And yeah, even some of the people in quantum physics and stuff, they're just like, oh yeah, I have an idea of the equations, but I never kind of take that step back of how it looks big picture. All right, more time on the clock. All right, hell yeah. Now I haven't really even thought of this part, but okay, so we talked about the oranges pyramid and how that was kind of similar to the sun. You know what I mean? Having this, you know, the sun being a pile of oranges, and then just out here. So this double slit, what I would say, is instantly starts, you know what I mean, in an Egyptian pyramid or a sun full of oranges, right at those two places. And then from those two places, so let's draw that. So even though you got this huge laser coming in, sure, it's going through there, but still, we're not talking one photon. Again, we're not talking one photon. I mean, obviously, if you see strips of light, you're talking about a hell of a lot of photons. So when it goes through these two slits, you know, even if they're small, I mean, we're talking the Egyptian pyramid of oranges and the sun full of oranges. And guess what? I mean, it's going to be, you're going to have these circles, you know what I mean? So, I mean, yeah, this, let's say this is half the height. This is a quarter of the height. You know what I mean? But that's still just, if you compare it to like the sun's energy and stuff, you know what I mean? And then, so this is where you get, you know, you're not talking one photon. One photon, hell yeah, can only travel in one direction. But if you have like a, and maybe I'm totally wrong about this, but I think this is where the double slit experiment probably gets too much credit, because you're not taking this one photon and throwing it through one slit and taking this other photon and throwing it through the other slit. And because you can't, one photon is, you know, it'd be like, oh, let's take one hydrogen atom through here and one hydrogen atom through here, and then let's say over here we see 4 hydrogen atoms. Like, that don't make sense, you know what I mean? Like that. So the same thing. You're taking one photon through here, one photon through here. You can't have more than 2 places observing 2 photons. But if you take a whole brick of photons, you know what I mean, then you kind of have this wave nature. Yeah, and so, yeah, man. And it's interesting. And I'll have to look at the term scattering, because one photon can't scatter. It can hit like an opposing electron and kind of change direction. But I guess that's scattering. And to put in full perspective, if you have a neutron star, which are just like absolute crazy magnets, it can shift. It can have shifts on a photon in space. It can change the direction of a photon in space. Okay, cool. But anyway, I don't know. You know what I mean? It seems like an obvious one. Why? But I just think the experiment's flawed. Like, there's no way you could have a slit that's tiny enough where only one photon width can go through, and so you have a vertical, because that's the thing. To have a vertical column of photons go through a slit that's just only one photon width in width, you know, I don't know. Because maybe in this scenario, it's the same as, that's my question. I think in the end, having intelligent questions is probably a more satisfactory end to a video. If you have, even if you just had 2 photons stacked on each other, it'd be like the same thing. You throw a photon here and a photon there and a photon there, you're still going to get 4 photons that hit the wall. And even if they're stacked in a vertical line. But you don't. You have more than one width of photons here. And then so you essentially, even though the slit is a slit and we think, oh, it's narrow and stuff, it's still an origin. So I think my analogy of getting back to the sun of oranges and the pyramid of oranges and then spilling out in all directions due to their normal directions anyway. But obviously, yeah, there's plenty of videos where, yeah, if these build up, hell yeah, there's light, and when they cancel, or if they cancel out, there's probably no light, if they actually, you know what I mean. But then, yeah, I think that's sufficient enough to understand that, yes, waves travel at the speed of light. When they hit other waves, they either double in size or they cancel. Like, all those rules apply. And, yep. I don't know. So yeah. I mean, people that think light is a particle, I don't know. Like, yeah, that's why it's just like, oh, because it travels from the sun. It's like, no, the wave travels from the sun. You know what I mean? The actual, and it's massless anyway. So, you know, the idea that you have, oh, this, you know, stuff's traveling through the universe. Well, it's just the waves. Anyway, I think I'm done because I don't really sufficiently answer the question, and that's all right. I'll throw in the. I'm not going to say words that don't make sense to me, and so I think I did a good enough job though. But that's my analysis. Those are the things I think about. I want to go right to what is light. It's on a spectrum of electromagnetic radiation, and sure, that's the other thing is like you can have a so if you do have an atom and it does emit radiation, well, cool. That's waves. And those are subatomic particles, too. So you do have, so anything that's emitted by a, yeah, and a proton is a subatomic particle. It's just a subatomic particle that's massless. So just having a good definition of these, I don't know, make it less, I don't know, magical. You know what I mean? But anyway, I gotta throw in the towel on that one. And maybe it is. Maybe this is. I'll have to talk to my brother. Just, are you still impressed with the double slit experiment? I mean, does that just rock your world? And why? Because it really doesn't. Because you just like, well, we just spend so much time looking at a mass, you know, compared to just a wave. Anyway, all right, I'm gonna be done. Thanks for joining me, and that's a video.